warming of Earth's surface under the mechanisms we understand causing that warming, namely the greenhouse effect, which I will elaborate again in later lectures. Under the greenhouse effect, one expects a warming of the surface to be accompanied by a cooling of the upper atmosphere. In fact, the temperature difference between the surface and the upper atmosphere is part of what drives greenhouse warming. And so if the Earth warms, you expect, ironically, that the stratosphere will cool. And the more the Earth warms at the surface, the more the stratosphere should cool, and the more that temperature difference between the lower levels of the atmosphere and the surface and the stratosphere. And in fact, we see that. The stratosphere has cooled substantially and the troposphere has warmed, and so has the surface. Now, Earth has many spheres. It's got the biosphere, the sphere where life lives. It's got the atmosphere, the gaseous layer. It's got the lithosphere, the rocks. It's also got the cryosphere, as in cryogenic, cryostat, these words meaning cold. And Earth has a cryosphere. The cryosphere refers to the ice and snow that exist at the surface of the Earth, some of it in the form of ice caps on places like Greenland and Antarctica, some of it in the form of floating sea ice, some of it in the form of mountain glaciers, some of it in the form of the seasonal ice and snow that falls in the temperate climates, and so on. The cryosphere. And the cryosphere, the ice and snow layers of the Earth, respond to changing temperature. And as you know, if you've ever left an ice cube out on the counter or something, it takes a while to melt ice. You put an ice cube out on your counter in your 68-degree-Fahrenheit house, and it doesn't instantly turn into liquid water. There's a lot of energy involved in changing the state of water from solid to liquid. So it takes a long time, it takes a lot of energy, and as a result of that, these changes occur slowly. And they, therefore, like the borehole temperatures, are indicative of long-term trends in climate. They don't tell you what's happening from year to year or month to month. They look at long-term trends because it takes so much energy to melt ice that the melting occurs over very long periods of time. Now, if you look at mountain glaciers around the world, take pictures of them from a few decades ago, take pictures of them in recent years, you will find that in many, many cases, you find substantial and dramatic retreat of glaciers. In the Cascade Mountains of Washington, for example, there are glaciers that in the 1920s extended, filled entire valleys. And if you take a picture of those glaciers today, you find they've retreated substantially up their valleys. There's far less area of ice. The ice is far less thick. Same thing in Alaska, for example. There are places where in the 1940s, as recently as the middle of the 20th century, glaciers filled whole valleys. Today there are lakes where those glaciers were. And way at the far end of the lake, you can see just the little bit of ice that's left of that glacier. Even tropical mountain glaciers, places like Mount Kilimanjaro, that have substantial ice caps on near their summits, even though they're in equatorial latitudes, those are diminishing rapidly, shrinking in area and thickness. So the mountain glaciers around the world seem to be, by and large, shrinking. Now, science is subtle, and there are other effects besides the warming of the planet that affect some of these things. And what a glacier does is determined by a balance between its melting or its calving off of ice at the point where it reaches the sea, if it does, and the accumulation of snowfall on the glacier. And one of the effects of climate change may be to cause more precipitation. And so some glaciers, depending on exactly how they're situated, may actually grow under global warming because they get more precipitation falling as snow and adding to the glacier. So these things are subtle. And a glacier that is bucking the trend of most mountain glaciers to be shrinking is not a counter-indication. It says, let's look at this glacier and understand what its particular circumstances are. If you do look at a whole lot of glaciers, if you were to make a graph, for example, of what a whole lot of glaciers have been doing over the past decades or even a century or so, you would find that most mountain glaciers' lengths remained relatively constant until a few decades ago, and then most, again, not all, began declining in length of the glacier, which is one measure of a glacier's extent. Another measure is its area, another measure is the thickness, another measure is the volume of the ice. But if you simply looked at the length of glaciers, and scientists have done this, tracking glaciers all around the world, you will find glacier lengths have tended to decline, and the decline has been particularly steep in recent decades, time that coincides with that steep increase in world temperature that I showed you in Lecture 1. So most mountain glaciers are retreating. A very different kind of ice is Arctic sea ice. Arctic sea ice is floating ice in the Arctic Ocean. Of course, in the Arctic, we have ocean at the North Pole, we have continent at the South Pole, so the two Arctic regions, the Antarctic and the Arctic, are very different geographically and climatologically. And in the Arctic, the floating sea ice is shrinking substantially. And if you, for instance, looked at pictures of Arctic sea ice, and you look particularly in September, which is about the time the ice has reached its minimum area, you will see, again, over a time scale of only 20, 30 years, you will see substantial decreases in the extent of the Arctic sea ice over that time. The minimum ice cover, make a picture based on satellite imaging, and the minimum ice cover is substantially lower at the present than it was 20, 30 years ago. The Arctic sea ice is diminishing in extent. It's also diminishing in thickness. We know this from declassified information from nuclear submarines that ply their way underneath the Arctic ice and did so in the 1950s and 60s. So they got measurements of the thickness of the sea ice from below, and we know that the thickness of the ice is also decreasing. If you were to make a movie, put together a bunch of data here and make a movie of it, you would see the Arctic sea ice gradually decreasing. You would see it some years it grows, some years it shrinks, but overall the trend is a decrease in the Arctic sea ice, in the extent of the Arctic sea ice. And that trend shows you, as the ice blows around and expands sometimes and contracts sometimes, that overall we're losing ice. Overall something is happening to supply enough energy to turn that ice into liquid water. I am going to show you one graph here. And you audio people, this graph is in your booklet, so take a look at it. These are measurements of the areal extent, the area of the Arctic sea ice over time since the 1970s. And measurements are taken every year at what's called the minimum ice extent. It typically occurs in late summer, early fall, typically sometime in September. And this graph shows the measures of that area, and the area has dropped substantially, something on the order of 30% or so, again the time since these accurate measurements were taken in the 1970s. It's a steep downward trend. It has accelerated somewhat in recent years. Again, as with all scientific data, there's some fluctuations involved there. But the area of Arctic sea ice has been decreasing substantially. You may have heard a lot about ice in Greenland. Ice in Greenland represents a different kind of ice. That's an Arctic ice cap. That's ice that is on land. It's land-based ice. And in Greenland, ice has been melting at accelerating rates quite recently. There's been a bit of alarm about this. You get the sense that perhaps a large amount of Greenland is melting. Well, what we're measuring typically is how much of the surface layers are beginning to show melting rather than staying solid all year round. And those numbers are increasing dramatically. We aren't losing an enormous amount of ice yet, but the trend is upward, and it looks like Greenland is beginning to lose ice at a significant rate. So the Greenland ice cap is melting. The situation in Antarctica is a lot less clear. At the fringes, Antarctica is showing the effects you would expect from global warming, but the interior of Antarctica, being a very cold, dry, desert-like environment, if any precipitation falls in the interior, it doesn't melt. And even with substantial warming of the planet, the interior of Antarctica is nowhere near to the point where it melts. So it actually is accumulating snow. And if there's more precipitation associated with global climate change, Greenland, or Antarctica rather, may actually increase in the interior extent of its ice sheets or ice caps. But the regions near the margin of that continent are definitely showing the effects of warming. One particular concern we have with places like Antarctica and Greenland is as the ice begins to melt, meltwater can flow not only on the surface, but it can flow down through crevasses, and it can flow along on the bottom of the ice sheet between that and the rocks, and it can lubricate that region where before the ice sheets may have been locked rigidly to the rocks. Now that gets lubricated, and whole large pieces of ice sheet could then slide off the continents and into the ocean. And there's worry that that could be something that could precipitate an abrupt rise in sea level. It doesn't appear to be a substantial possibility in this century, although it could happen. And that's one of the worries associated with this melting. There are other indicators, other fingerprints of global climate change. For example, if you track weather patterns over a few decades, there are changes. And again, I said in the first lecture, weather is different from climate. Weather is the day-to-day stuff that's happening in the atmosphere, but if you look at the trends in weather over the decades, that tells you something about what's happening to climate. And what are some of these changes?